ASDIP RETAIN includes the design of gravity retaining walls, but how do you actually design these kind of structures? What stability failure modes control the design? How do you check the structural capacity of the members? What code provisions are applicable in this kind of design? This is Javier Encinas, and today we're going to design completely from scratch a gravity retaining wall example using ASDIP RETAIN. Let's get started. As an example, consider this retaining wall, which is 8 feet high, is supporting a flat backfill. The properties of the backfill are density, 120 PCF, phi, the internal friction angle, is 28 degrees, the materials, plain concrete, F'C, 3 KSI, and Fy is 60 KSI in case that we need any rebars. The allowable soil bearing pressure of the natural soil is 3 KSF. With this information, we need to design the structure, we need to find the dimensions, check the stability failure modes, check the structural capacity of the members, and complete the design. Let's go to ASDIP RETAIN. When you open ASDIP RETAIN, you see the project manager. Here you can see the modules included in the package: cantilever retaining walls, counterfort retaining walls, basement retaining walls, sheet piling, and gravity retaining walls. In this case, we're going to design a gravity retaining wall, so let's create a calculation. Let's call it example. And the calculation has been added to the tree. Double click on the node, and this is the template of the gravity retaining wall design in ASDIP RETAIN. At the left, you enter the information, at the right, you see the results. All the information regarding the dimensions are entered here. If we click on the Graph tab, we can see graphically what we are doing. For now, let's assume that the wall doesn't have any additional concrete footing, just the stem. From the statement of the problem, we know that the height is 8 feet. For now, let's assume that is 1 foot at the top and 5 feet at the bottom. Let's go to the backfill and cover tab. Here the backfill height is a little bit lower than the wall, so let's say that is 7.6, 6 inches below the top of the wall. It's a flat backfill, 0 degrees, and the soil cover at the front of the wall is 1 foot. Let's go to the loads tab. Here the backfill density is 120 PCF. We will use the Coulomb active pressure theory. The internal friction angle is 28 degrees, and the water table is 5 feet above the base of the wall. All this information was given in the statement of the problem. Let's go to the materials tab. Here at the stem, the concrete F'C is 3 KSI. Let's go to the bearing soil tab. The allowable soil bearing pressure is 3 KSF. Friction coefficient 0.5, and the rest of the values are correct. So we have entered all the information given in the statement of the problem. Let's see how the results look. Let's go to the at a glance tab. This is a summary of the results. Here we can see immediately that there are some failures, particularly the sliding safety factor 1.05, which is less than 1.50, the minimum. So this check is not passing. We need to add more weight to increase the sliding resistance. Let's go back to the gravity wall. Let's add a concrete footing underneath this wall, like this. For now, let's assume that is 1 foot thick, and at the top is 1 foot wide, and at the heel is 1 foot wide. With this additional weight, the sliding safety factor now is 1.42, but it's still less than 1.50. We need even more weight. Now the wall looks like that. Let's increase the size of the wall at the base. Instead of 2 feet and 2 feet, let's say 2.5 and 2.5 here. So now the wall is a little bit wider than it was before, additional weight. Let's see the results. Now the sliding safety factor is 1.56, so it's perfect now, it's just over 1.50. The bearing pressures are maximum 1.1 and the allowable bearing pressure is 3.0, so it's passing. The shear forces for the different members, the ratios are very small, very comfortable, everything is passing. And the structural capacity here for the different members, there are some issues. All these issues, for example, are related to the steel area. So we are assuming that the footing is reinforced. That can be seen here. The footing is reinforced. We can specify that it's not reinforced, that is just plain concrete. Let's go to the reinforcement tab. We can uncheck this checkbox, reinforcement provided. We uncheck it, and now it's unreinforced, just plain concrete. So all these checks for the rebars are not shown, are not applicable anymore, and everything is passing in this design. If we go to the Condensed tab, it's a more detailed set of calculations grouped by topic: soil bearing pressures, backfill properties. This is the overturning calculations, overturning and resisting. And this is the overturning safety factor, 5.7. It's very comfortable, it's more than 1.50. The sliding calculations for this controlling load combination, in service load combination. This is the friction force at the base, 3.1 kPa. And this is the contribution of the passive pressure, 0.5. So the sliding safety factor is 1.56, which is more than 1.50, is passing. Here is the stem design for the controlling factor load combination. Please note that even when the stem and the footing are plain concrete, they are designed per the ultimate strength design method in ACI. There's a chapter in ACI for plain concrete, so the program uses those provisions in this design. So the ratios for the stem design are very small. Here is the design of the heel, also the ratio is very small as well, and the toe design as well. So basically the structural capacity of the different members, stem, heel and toe, are not controlling the design. This is pretty common in this kind of structure. It's unlikely that in a gravity retaining wall, the moment capacity and the shear capacity will control the design. We can see that, for example, if we go to the graph tab, the stem tab, the program shows the moment diagram and the shear diagram. The blue area represents the structural capacity, and the red lines are the actual bending moments and shear forces at the wall. If we go to the detail tab, here we can see a more detailed set of calculations, step by step, with exposed formulas, also with references to the ACI code, the overturning calculations, step by step, for granular checking, the soil bearing pressure calculation with the controlling combination, service combination, here the sliding calculation, service combination as well, and here the stem design for factor load combinations with all the corresponding provisions in the ACI code. All the references are noted there. Heel design and toe design. Graphically, we go to the overturning tab. These images show the pressure diagrams applicable to the overturning calculations, so the active pressures and the water pressure, and at the bottom the forces used in the calculation of the overturning safety factor. All these calculations can be sorted by load combination. Let's go to the sliding tab. Here the program shows the pressure diagrams applicable to the sliding calculations, passive pressure, active pressure, and the water pressure. And at the bottom the forces used in the calculations of the sliding, including the friction at the bottom and passive at the left. In the bearing tab, the program shows all the pressures that are applicable to the bearing analysis, active pressure, water pressure, and the bearing pressure at the bottom of of the footing. At the bottom, you see the forces included in this analysis, including the reaction at the bottom with eccentricity. We go to the STEM tab. The program shows the pressures diagram that are applicable to the STEM design, active pressure and water pressure. And the program shows the bending diagram and the shear diagram as well. All this can be sorted by load combination per factor load combinations, and the program shows the design ratios for flexure and shear for the controlling load combination. All these ratios are very low in this case. Finally, in the construction tab, we can see the final design of this gravity retaining wall, all the footing dimensions, STEM dimensions, height, the water table. If we go to the design criteria, go to the codes, in this case we use ACI 318-19 and the load combinations are AS7-22. As you can see, it's very easy to design gravity retaining walls using ASDIP RETAIN. We were able to complete and optimize the design in just a few minutes, which otherwise probably would take much longer if we tried to do it by hand. If you like the software, please visit the website www.asdipsoft.com and download the free 15-day trial. Please subscribe to the channel if you want to receive notifications in the future for similar videos. Thank you for your attention.